Hi everyone, welcome to this new episode of Additive Talks. If you are joining us for the first time, make yourself comfortable. Additive Talks are simply a series of panels that focus on discussing the use of AI technologies in a given industry. If you've been here before, thank you for listening to our insights into the world of additive manufacturing. My name is Katie Sinze, Managing Editor at 3D Additive Media. Without further ado, I would like to give the floor to our experts so that they can introduce themselves as well as the company they represent. And I will start with you, Ryan. Can you please introduce yourself?
Sure. Hello, everyone. My name is Ryan Dayhoff. I wear two different roles at Oak Ridge National Laboratory. One, I'm the director of the Manufacturing Demonstration Facility, which is a Department of Energy sponsored facility related to advanced manufacturing technologies. And then my second role is that I also run a program or am the Oak Ridge National Laboratory contact on a program sponsored out of DOE's Office of Nuclear Energy called Advanced Materials Manufacturing Technology, specifically for the nuclear industry.
Thank you very much, Ryan. What about you, Adam? Who are you?
Hi, everyone. My name is Adam Travis, and I run the Additive Manufacturing Center of Excellence at Westinghouse. So my group is responsible for setting the global AM strategy within Westinghouse, where we see value in using AM, adopting AM, and then driving its implementation across the company.
And then the person that is really close to me in terms of geographic or religion, Benjamin, can you please tell us more about you?
Yeah, sure, Katie. Hey everyone, I'm Benjamin. I work at the nuclear power plant in Leibstadt, Switzerland. You can see it right behind me on the screen, having a beautiful location right near the German-Swiss border. I work there in the mechanical department and I lead a multi-purpose team. We deal with all different kind of fun applications ranging from condition monitoring to additive manufacturing to robotics to some special task projects which affect the safety and the availability of the plant. And yeah, multi-focus, multi-purpose, try to combine it to generate the added value for the plant and keep the plant running safely.
Well, thank you very much, Benjamin. Well, this is not the first time we actually talk about the use of AM in the nuclear industry. It's true, this is a niche industry. And 3 years ago, we had our very first conversation on the topic, as part of this Additive Talks series. And ORML was actually one of the speakers or around this virtual table. So my first question will be for you, Brian. When we first had this conversation, the market was still very nascent. The very first use case is being recorded in 2017. So taking into account the latest activities in your organization, what changed?
Yeah, so a lot's changed, I would say. I think one of the things, as a little bit of a background, I've been in the additive industry for a long time, over a decade. And what we see is that there's a constant push and development, improvement in the technology space.
Yes.
And I think a lot of people's mindset are really changing with some of the original developments or kind of some of the things that happened in 2017 with Westinghouse, with folks like Oak Ridge. And I think there's a level of confidence that is starting to happen across the industry where people are becoming more and more comfortable with additive technology. They're seeing it implemented in other industries in mass production, specifically aerospace and in critical applications. But now we're starting to get into this realm of we understand the technology and there's enough good work going on that we're starting to gain confidence in it, that we can use this in applications like nuclear. And so it's really exciting time, I think, to see those developments being made and how they're impacting our understanding and basically making it possible to utilize advanced manufacturing technologies in the nuclear industry.
Yeah. Well, you mentioned Westinghouse, and Westinghouse is one of actually the well-known names in the industry, especially in this field. So Adam, those who follow the advancements of AM know that your company, installed one of the first 3D printed parts in a nuclear power plant. It was a simple plug-in device, if I'm not mistaken. In a few words, when and how did you decide to start betting on additive manufacturing?
Yeah, so you're correct. The thermal plugging device was the first AM component that we installed. It actually has the distinction of being the first ever AM component installed into an operating commercial nuclear reactor, which is an achievement that we're extremely proud of, right, as an organization. That insertion happened in 2020, but Westinghouse's involvement and pursuit of AM, started many years before that, back in around 2013. And it all started with a pioneering engineer seeing AM at a conference and immediately recognizing the potential, bringing that back with him and just starting to agitate, right? Starting to push, internally to say, hey, let's see how we can use this. And so our approach from there has always been a metered one. So a series of small bets rather than one large bet. There's a lot of horror stories or examples out there, right, of companies that have bet very large on AM and kind of, if you build it, they will come mentality, right? And it doesn't always pan out. And so we've always been very intentional at Westinghouse about trying to build a sustainable AM program, right? One that grows as the value to the company grows, and making sure we keep things in check. So, the kind of the stages we went through was in 2015. We conducted our first AM material irradiation study at the MIT test reactor. With that, in a couple of years, right, we were able to confirm that AM materials hold up largely identically to conventional materials under irradiation. So that's the first big checkbox to say, we can move forward. From there, we moved into the thimble plugging device, as you said, which was really a demonstrator for the nuclear industry at large, right? To say that AM is ready, AM can do this, and to prove that, right, in very explicit terms. And then from there, we started designing our first value-add components, and those started getting inserted into reactors a couple of years ago, I think starting in 2022. And then just most recently, a few months ago, earlier this year, we celebrated our 1,000th in-use AM component being produced.
Yeah, I saw that. Congrats.
Yeah, thank you. This chart, right, of kind of incremental improvements or incrementally marching right towards the implementation of AM.
Yeah. Well, and you, Benjamin, please allow me to say KKL for Ken Craftwell, a lifestyle, because I'm not sure I have the right pronunciation for your organization. And it is one of the few things. It is one of the few nuclear power plants that decided to integrate AM within its mechanical engineering department. And I'm really glad that you're part of this virtual table, because I know, well, the very few nuclear power plants that we know actually rely on external service providers. So what led to this decision when we know that?
Yes, that is a very, very interesting topic for us for a long time already for multiple reasons. First of all, additive manufacturing provides you a lot of freedom, which in the engineering realm you do not have so much with conventional methods. So that is something where we started looking into a couple of years back when we were facing some challenges where we had to design a vibration mount and we could not traditionally manufacture that. So since then, we had found this very, very interesting, and we adopted the idea that this might be a part of the future. But let me explain a little bit more in detail what our approach here is, because it's this kind of a hybrid approach still at the moment. So we do not manufacture our own metallic components additively at the moment. So that is something where we do still rely on contractors as of today, but we do the design and the engineering in-house. That's the core knowledge which we built up here, and we're still working heavily. And Adam alluded a little bit to the challenge with irradiation. So there's a lot of challenges involved where we feel like, from the engineering background which we have in my team, that we understand what is the requirements to get this done in the nuclear business. But of course, we do not have the core technology to produce additive manufactured parts, so say by DED or laser powder bed fusion. So that is technology and experts around, which we of course rely heavily on. So in a nutshell, we have the hybrid approach still, that we design and engineer the components with the support, of course, of external experts, but the manufacturing is done still in a contractual space. But we're working on the concept, and a big concept. I think it's a bit too early to talk about that in detail, but we're looking into a lot of expansion cases, because just to give you a brief link here, KKL is running for almost 40 years now. That
Yeah.
is in the nuclear realm. Actually, it's still young plant. There's way older ones, and we're planning for, I shall say, for almost another 40 years of operation. So the obsolescence, so spare parts topics, contractors from the early age which are not on the market anymore. There's challenges around to get spare parts in time. The lead times are really high. The requirements from the regulator side are very high. So for nuclear qualified components, you sometimes need 5 years until you have them in house, and that is because there's not so many contractors anymore can build them in the conventional way. So just to span it a
Okay.
little bit, there's a lot going on with us where we strategize and think, how can we tackle the challenges of the future to have critical parts available on a short lead time?
Yeah. Well, I hope you will keep us posted.
I
So,
will.
yeah. Well, let's try to give the community a bit of context or introduction to this topic. What would be the key reasons that could foster the use of AM in the nuclear industry? I've heard so many things. I've heard improving nuclear security, enabling CO2 reduction in energy generations. I just don't know which one is true, which one is not. So, Adam, can you go first?
Certainly. So I'll speak maybe personally first.
First.
You,
Okay,
you,
good.
you talk about reducing CO2, right? And I was an AM guy before a nuclear guy, right? I started in AM and I
Really?
went with me to nuclear, right? I'm still learning a lot about nuclear, but what originally drew me to nuclear is if we look at the challenges ahead for the world, right, in combating climate change and reducing carbon emissions. If you look nuclear and other low carbon energy sources like wind and solar, right? Um, there's a metric that we use in for the energy industry for we call capacity factor, which is essentially a metric of uptime, right? If a energy plant can produce a certain amount of energy theoretically, how often is that plant up versus down? How often is it at full operating capacity versus partial? And looking at especially nuclear, wind, and solar, right? Wind and solar have very low capacity factors. I think it's somewhere like in the teens and in the 20s, right? Which makes sense if you think about it. The wind's not always blowing and the sun's not always shining. Nuclear, on the other hand, has the highest capacity factor of any energy source out there, right? Not only low carbon, but any coal, natural gas, all of them. Nuclear is, I believe, 93% on average, at least in the U.S. That number may be a little different globally, right? So when we think about a stable, low carbon energy grid and fulfilling that base load duty for low carbon, nuclear really stands alone, in my opinion, is being able to fulfill that role. And so I think there's extreme societal importance around not improving nuclear, and nuclear doesn't really have to improve from where it is, right, to fulfill that role, but certainly doing everything we can to modernize and to future proof and always drive higher efficiencies with nuclear. So within Westinghouse, that's kind of my personal side. But then within Westinghouse, right, our philosophy with AM is we're always looking to do things with AM that were not possible before, right? Things we couldn't do conventionally, and where does AM open up new opportunities for us? So one really explicit example I can give is debris filtration in the existing fleet of light water reactors in the world, in boiling water reactors specifically. And actually, before I get into this, I want to clarify for the non-nuclear audience that may be listening that the coolant loop for a nuclear power plant is an extremely clean environment, right? So I don't when I talk about debris in the coolant loop, I don't want to give the impression that this is the false impression that this is a dirty environment, right? That said, right, these are very fine-tuned machines, and so very, very small pieces of debris can cause damage. And so there's data that says that pieces of debris down to even a 5 millimeter fragment of wire, not 5 millimeter diameter, but just a sliver of wire 5 millimeters in length can fret, can wear on a fuel rod as it's circling through the coolant loop, and over time, in the rarest cases, can actually wear through that fuel rod and cause uranium fuel to leak out into the coolant loop. So with conventional methods, Westinghouse was able to achieve 100% filtration down to 7 millimeters, which is very good, but obviously still leaves a small gap there where there's at least a theoretical possibility of debris that could cause damage in the long run. With AM, we were able to come in and improve that and actually achieve 100% filtration down to 5 millimeters and essentially mitigate,
which is very good,
that possible failure mode. Yeah. And then, when we look to future advanced reactors like the Vinci microreactor or the Astro Vinci lunar reactor, the use cases and the possibilities for AM really just go wild.
Yeah, and I can see that Ryan was nodding, so he approves. I mean, he approves some of the things that you were saying. Ryan, do you have another insight into this question?
Yeah, so I think that there's a lot of interesting things that are happening in the additive world that could help nuclear, right? In certain ways. One of the things that we've been working on is, and I think Westinghouse, as they talk about the number of parts that they've put in service, they have this tackled to a large degree. But how do you certify and qualify kind of these new advanced manufacturing technologies that people want to use in the nuclear industry? And I think one of the unique things about additive manufacturing is you have the ability to inspect or use a lot of in situ process monitoring while you're building the part to understand how that part was created. And that data is very available, it's very usable, and that can, I think, really help aid in the certification and qualification of components. I don't think we're going to completely eliminate any of the conventional inspection methodologies today. But as you generate more data and generate more process understanding, we start to see that there's very good agreement, potentially less variability with additive manufacturing than some of the other conventionally manufactured processes. And so I think that there's a real opportunity in the future to use this kind of data-driven approach to drive down some of the manufacturing costs and some of the certification and qualification costs that are generally responsible for driving up the cost of some of the components fabricated. So I think that there's a really unique opportunity there to do things maybe even better than we've done in the past. So I think that's a particularly unique thing about it.
Yeah. What about you, Benjamin? What's your take here?
Yeah, so my one is a little bit plus and a minus in a box, because in the first place, nuclear doesn't need additive to be successful. That is a very bold statement, which I need to say. We always manage it without same. Yes, same as the way as we never relied on robotics and drones and quadruped as much as we love these ones, but we do not need them to be successful. But on the other hand side, having that said, I totally agree with Adam and Ryan, and I think many people see that there's a great potential to make things easier, and especially in a cost-sensitive environment as we are in today, where safety is, of course, always the first priority. And working for a utility, I need to emphasize that as many times as I potentially can. That is always the highest priority above any economics and business case. But at the end of the day, we heard that there's other means of electricity production. So solar, wind, when they become too competitive, there's a stage when you're not going to build any nuclear power plants anymore if the abundance and the availability is just there. So in the end, it is, of course, something like additives is something which makes the nuclear case a very, very compelling case because
Yeah.
you, as I mentioned before, can cut down the lead times substantially. However, there's challenges left to solve, and we just touched briefly on them. So qualifications, certifications of all kinds of means, the long-term operation experience of these components. So just to touch a few of them. So at the end of the day, I definitely agree and shall say additive and nuclear work very, very well together. And additive is an enabler for a lot of things in the nuclear sector. So I'm very, very strongly committed to this and working hard that we can get this into practice. But yeah, there's a long way ahead of us. And until we can say that you have a break-even point, like even from a fiscal aspect, financial aspect, that takes still some time because material qualification costs a lot. And you need to qualify and certify your contractors to the nuclear standards. They're very, very high. But if you've done this once, you have a huge benefit there. The second and third time you do this, they're going to be way more cost efficient and compelling. So at the beginning, it's a very huge invest, I would say, and the break-even point takes still a lot of years ahead of us, but it will be there because nuclear, we heard it before, will always be part of the mixture, and I'm totally convinced of that. And to make it cost compelling, I shall say additive is a definite help for this in the long run.
Okay. Thanks. I can see that we've started receiving a lot of questions from the audience. We pause in about 10 minutes to answer all of them. So please, you can keep, writing in the Q&A chat in front of your screen. In about 10 minutes, we'll pause and we'll read them so that Adam, Benjamin, and Ryan can answer all of them. So Benjamin, you you were talking about your business model, at the beginning, and I wanted to have a slight, overview of how things work, when you are an insider in a nuclear power plant. What are the hidden complexities that external service provider may not always see or take into account when exploring AM, according to you?
Yes, I mean, it's same story as with any other technology. The expectations are very, very high. So the
Yes.
nuclear industry has a little trait that let's say, we're being talked about when things go south. So we do not talk much about when things go the right way. So if you want to really have someone understand what is going on behind the closed doors, that takes a long time. And the cycle, I mean, we have different cycles all around the world, but the cycle is a year where we have an outage of roughly a month, plus minus, depends on the local requirements. And then you have 11 months of operations. Sometimes you have 23 months of operation, depending on where you are. But to understand what that means, after the outage is before the outage, that you have only a 1 month and minus the prep and the end work, where you can bring things into the power plant, do modifications, that you really need to align everything exactly on that date. And it means everything. And if there's the slightest doubt that something doesn't work, you will postpone it a year. And that is something which I personally find a lot of contractors do not understand right from the beginning, especially not having the nuclear experience. And then, of course, it's extremely challenging to get all the papers right, the certs and the qualifications, what you need to do. And especially in the AM corner, it's fair to say all these provisions do not exist yet. So we start with low safety relevant components where we can introduce without any risk to the nuclear safety and work our way up. And there's organizations supporting on these and doing a lot of work with all the manufacturers and the laboratories out there. So to have someone, let's say, from the local market who serves other industries, needs to be onboarded over a long period of time to get the intricacies of the nuclear. And I'm not speaking about the specifics of how a power plant functions, but this is a different story.
Yeah. Okay. I don't want to ask Adam if he agrees with you on that. I really want us to quickly jump directly into the technical challenges, because I can see we also have a lot of questions on that aspect in the Q&A chat. And Ryan, that question will be for you first, before Adam adds his perspective. 2 years ago, materials validation was listed as the primary challenge that slowed down the adoption of AM within this field. Why is that? And would you say it is still the case today?
I think we're getting a lot better at
Okay.
understanding those challenges.
Yes.
And I think part of what's happened is I'll kind of use some personal experience, maybe from my time at Oak Ridge. But one of the things that additive really stemmed from was this idea of rapid prototyping, right? So if you go back 10 years, 20 years, people were doing rapid prototypes, and really what's important in that context is the geometry of the part, right? And so if you can get the right geometry, then that serves the function that you need for a prototype. However, when you start saying, can I actually take that geometry and put it into functioning service, then you have to worry about the performance of that material. And really that performance is governed by microstructure and composition and all the things that a conventional material is governed by, right? And so what happens in the additive process, because of the complexity of the process, that can lead to variability of different mechanical properties and performance as a function of the geometry of your component, right? And so historically, people were focused on getting geometry, and that meant, and then they figured out that when I actually dig into this, the properties of a thin wall might not be the same as the properties of a thick wall, might not be the properties of geometry A versus geometry B. And I think what's happening is people realize and acknowledge that variability now, and are doing a lot of research to understand where the variability is, how does the processing parameters link to that variability, and how do I control that variability, right? And how do I make sure that I'm going to get the mechanical properties in a component as expected, and what level of degree of certainty I will have those properties. And so that research is really being conducted that is helping to say, yeah, we can guarantee with this level of certainty that we're going to get this performance in these geometries. I think the challenge is when you go from one geometry to another geometry to another geometry, you have to still assess that. However, the more you do that, the better you get at it, right? It's the same thing that's happened, and we've seen a lot of talks. I actually watched a really interesting talk a couple weeks, or I guess a couple months ago, at the NRC hosted a workshop, and somebody said everybody talks about variability in additive manufacturing. We have variability in rolled product, we have variability in forgings, we have variability in castings. We know this, we just know how to deal with it. And so I think there's been a real challenge over the past couple of years in the additive community to help develop the tools and the knowledge to assess that variability for additive. And so that is enabling us to use that in different applications.
Okay.
So I think that's kind of, there's been a massive amount of research in that area that has really helped companies and people understand where that source of variability is and how we deal with it.
I definitely need to underline this. I like your comment there, because it's exactly right. Subtractive manufacturing, casting, they have these exact same challenges, but nobody talks about it. Nobody talks about the CNC guy being qualified to some standards. You always look at the product, but in the AM business, you try to make a different use case, and that's things which I don't like. That's over the top. So data-driven is definitely the key here.
Well, Adam, do you want to add something here?
Yeah, just from maybe the opposite end of the perspective spectrum here. We're reaching a point where in some areas in our AM program we're looking past adoption and into scaling, right? And so then we start to grapple with these questions of how do we grow AM by volume, right? Not by affiliating applications in operation, but how do we actually grow volumes? And we're presented with this challenge that is, I think, somewhat unique to nuclear within the AM sphere, at least, in that, when we go look at a lot of AM contract manufacturers, they're very heavily into aerospace, space, and defense. And so you see a lot of AS 9100 and comparable, QMSs and quality systems. Nuclear operates to, at least in the US, right, under the NRC, operates to what we call NQA 1, Nuclear Quality Assurance 1, right? And that varies by country and by regulator. that's our closest analog to AS9100. And by default, as you would imagine, right, there's not a lot or hardly any AM contract manufacturers that operate to NQA1. That's not a trivial task to
Yeah.
elevate someone to NQA1, even if they're already operating at AS9100. So we grapple with this somewhat philosophical question. Is it easier or better to take an AM supplier and turn them into a nuclear supplier, or take a nuclear supplier and turn them into an AM supplier? We've done both. We're currently actively doing both. I don't know that there's one right answer to that, but certainly a challenge that I think the industry is going to have to grapple with as more and more of these applications come online and volumes continue to grow.
Okay, good. Let's pause for a minute and let's try to answer a couple of questions from the audience. I will start with comment number 3 from Pranav. How does the nuclear sector select the materials suitable for AM, especially metals? I think the question is a little bit in line with what we discussed right now. So I don't know if Ryan wants to have a take, or Benjamin, do you want to have a take first? This question?
Yeah, I can take the question first, and then others are definitely entitled to add there. So yeah, how do we select materials? Of course, the AM process is same like with welding processes, having some limitations on the materials and chemical compositions which you prefer to use there. When it comes to, let's say, speaking my applications, I look into the, let's say, high grades. So like an Inconel 718, for example, and other high, let's say, ductility, high strength materials, because looking into the perspective, what we need is we want to replace castings, and castings are very often very, let's say, low grade materials. They just increased the wall thickness 40-50 years ago, so it doesn't matter how much is your yield strength, actually you compensate it with wall thickness of your valve, for example. So that is something which is very easy to find a superior material to. So if it's like the typical casting metals there, that you substitute that with Inconel, for example. However, you need to look into other things like that. You don't have the electrical corrosion issues there from ferritic and austenitic. So what we are looking into, and by no means we are finished with our survey here, is what we have as typical materials used in the Switzerland here for the ferritic corner, for the austenitic corner, for the nickel base, for the bolting materials. And we have potential candidates for each of them where we say, okay, they are superior in the mechanical properties, and we do see potential that we can qualify them for. So the approach is rather like what has been done in the past, and like for like replacement in the geometry, but with better material properties for just replacing the existing parts where needed.
Thanks. And then let's try to be a little bit brave, just to, in order to answer all the questions, within the time frame. Adam, do you have a different perspective on the selection of materials for the nuclear?
From our side, all of our early applications, we stuck to very well-established materials, within the nuclear sphere. So 316L, nuclear grade 316L, and Inconel 718, right? A718. Those are the first two big ones, right? And kind of as Ryan touched on, there's a lot of work in qualifying the process, and then there's also a lot of work in qualifying new materials. And then trying to tackle both of those at once is really a huge mound, a huge battle, right? So we said, let's focus on the technology, use tried and true materials, but certainly there are longer lead projects underway at Westinghouse and throughout the industry looking at novel materials, more exotic materials, high performance materials.
Okay. I think Pranav had a comment for Benjamin in the Q&A chat. But first, Ryan, do you have another take on these questions about the selection of materials?
Yeah, so we're a little bit more focused on the research side, right? Yeah. So within the AMMT program, one of the things that we really set out to do is try to accelerate that qualification process for components. And so to do that, by this data-driven approach, we kind of took the same approach, I think, as Adam and Westinghouse. We said, let's take a material that isn't completely off the wall and try and certify and qualify it. So we're really focused on 316H material. There's been a lot of work on 316L. I think we know where those applications are. 316H is a material that I think is, we've had a lot of feedback from different industrial partners operating different reactor types, that is kind of a universal material that would be beneficial to the industry. And so our main focus is on that material. We do have a lot of other work and examples where we're kind of exploring a wide range of nickel-based alloys, ferritics, martensitic, even refractory metals, to understand how they may impact different nuclear reactor types, right? So I think I'm similar to Adam. I don't come from a nuclear background. I come from an additive background. The more I'm getting into nuclear, the more I see that there are a lot of different benefits across all different material types for specific reactors. And so we're in the process of evaluating and prioritizing which materials we work on. I think refractories is going to be an interesting one, potentially for some of like the molten salt type reactors. But even, nickels, there's the challenge I think really becomes is, are these materials suitable and compatible in additive processes? And what modifications do you have to make to the process or the chemistry in order to get the right material properties that you need in a specific component?
Okay. Well, question number 6 from Taron. From a DED perspective, what are the most suitable and applicable standards for nuclear applications with AM? Adam, do you want to go here?
I think that was me. Yeah, so for DED, again, like we did with materials, right? We tried to use tried and true materials in our initial applications. We also focused on laser powder bed fusion for our initial application, right? Which is, I would argue, the most, probably the most, well, depending on your metrics, but I would say the most mature, at least the most prolific, right, of the AM modalities out there at the moment. So we focused on that. We certainly see DED, especially wire DED, as really the next big focus area, both within Westinghouse and within the industry. The big one in my mind, and maybe this isn't DED specific, but is the ASME boiler and pressure vessel code, right? So there's a lot of really interesting components and geometries out there that we would love to print that fall under the BPV code. That would fall into the wire DED category. And so looking ahead to that incorporation into the code, it will open up a lot of additional opportunities.
Okay. Ryan, any other takes here?
Yeah, I agree with Adam. I think what, at least from my understanding, is that they're in process of performing or going through and evaluating that code case for large scale DED. And so I think that will be a really big step forward. And I'm hoping that we see some traction in the next, I would say 6 months to a year on where that stands. I don't know the exact dates. I'm probably not allowed to say if I did. But I know that there's a lot of work going on there to understand how you certify and qualify DED processes. And in some ways, I think in some ways people are more comfortable with the DED technology and the standards that are out there because it is more similar to welding or multi-pass welding, at least from a physics perspective and a solidification and the materials perspective. I think it's more similar than some of the laser powder bed fusion that have more rapid solidification than you may expect in a traditional weld. And so that level of comfort, I think, is starting to get people geared towards those standards and making them.
Well, comment number 8, Darren continues with the very big questions. Don't know if you will have time to answer it here. What are some of the disadvantages of additive manufacturing for the nuclear sector? Benjamin, I would like to hear you first here.
Yeah, I mean, biggest disadvantage is that you don't have any code yet. And the asthma boiler pressure vessel code was mentioned before. Our primary circuits are also designed according to these rules. So the biggest disadvantage is that if you want to use AM for manufacturing a component of these types of safety classes, you basically start in nowhere. Talking about the advantages which you have later on, yes, you need to overcome the obstacles which you have right at the beginning. And what Ryan was alluding before to is clearly the DED is in favor. So that is a personal disadvantage to myself. Let's say I'm a powder bed fan, a great fan of this technology, but I've seen over the last 1.5 years that the adoption of the code cases for the asthma boiler pressure vessel code is definitely favoring the DED. And from a technical perspective, Ryan, you told it absolutely right. Totally agreed. It is quite related to the PQRs and stuff what you do there on the wire welding corner. But I think that is very close call here now that you can say that is coming as a code case, and you can start manufacturing components here. In a couple of years, you will have it in the main code. On the powder bed fusion side, I'm not so sure how long that's going to take, because also the Electrical Power Research Institute, which is a great organization supporting the nuclear utilities here, sees the same struggle here. So I would say there's a lot of push necessary to get the powder bed fusion into the same realm as the DED from a code perspective. But I personally spent my effort on the powder bed because, as I said, I'm definitely a great fan of this in terms of the design flexibility. Though it has its own challenges, but if we need to qualify something at our own expense, we will definitely go for the powder bed, because the others cover the DED case. There's nothing where we need to look into. There's others way ahead in the game, but not on the powder bed.
Well, if you have DED manufacturers in the audience, they will be disappointed right now. And do you have, I mean, are there any other disadvantages of AM for the nuclear sector that you mentioned here for Tyrone?
Was that disadvantages? Was that the question?
Yeah, number 8. Yes.
Yeah.
Disadvantages.
So yeah, I think, I don't know if I call it a disadvantage, but certainly the misconception that we've had to fight internally from the Center of Excellence is AM as a magic bullet, right? I can get anything, anywhere, anytime, especially how I can print it and it's ready to go in a week. That's not how any manufacturing process works. So we've had to fight back against that misconception that AM can solve any problem, right? AM has some very specific advantages to it. And I think I touched on this, but chief to us is design freedom, right? I don't like the term design for AM because it sounds limiting. I like to say design for purpose, right? We should always be designing parts for their purpose. And if AM allows you to do that better than any other process, that's a really good starting place to build a business case for AM, right? So that's the chief advantage that we see for AM. But and Benjamin's mileage with this may vary. But from our perspective, right, there have been some industries and companies that have made use of AM as a supply chain tool, a manufacturing tool than a design tool. And for Westinghouse and the businesses that the spaces we operate in, we've just found that's not the case for us. It's really a design tool and improving the performance of components and assemblies in ways that we couldn't before.
Okay. Question number 9 from David. 15 more minutes left. What if you could print fissile material? Would that be an advantage, Dr. Ryan?
Yes.
I'm going to hand it over to Adam.
Yeah. So there's work underway in that direction. There's a handful of projects looking at metallic fuels, printing metallic fuels, and at least 1 or 2 looking at ceramic fuels as well. Can't say much more than that, but that's certainly a lot of promise, a lot of potential in that area, and something that multiple groups are looking at.
Okay, good. And then we have question number 10 from Devon. Yeah, Devon from South Africa. Oh, good. We have installed a system at the research reactor facility, and we use AM for printing parts for particle accelerators. I would like to know if people are using radioactive materials or unconventional materials in LPBF to make parts needed in the nuclear process. We have also had inquiries on fuel roads and would like to know if this direction is warranted.
So I read this as similar to the last question: radioactive materials, fissile materials. Same answer. There's some work underway. It's still fairly in the laboratory, so to speak, looking at fissile materials, but certainly a big area of interest. On the fuel rods, that's an interesting angle. We were actually posed the same question internally, and we said no. Undeniably, no. It's a long cylinder, right? It's not a geometry ideally suited for AM. So geometrically, I would say fuel rods don't make a lot of sense.
Yeah. Dr. Dehop, do you want to add something?
Yeah, I think I would say I completely agree with Adam. I think looking way into the future, we have had some people look at non-conventional geometries of different reactor components, and how would you could you potentially optimize things if you could print fuel rods, if you could kind of redesign all the reactors from scratch? Would you still have the same thing, or do the reactors look a certain way because of the design and manufacturing constraints that we had when they were designed 50 years ago, right? And the answer is I'm not sure that I think we know yet. I still think that that's an R&D type endeavor. I think that we've seen some opportunity for maybe improvements, but I'm not sure that anybody's really convinced that doing that is the highest priority level thing today.
Yeah. Benjamin.
Yes, I totally agree in the sense that only because you can print it that you need to print it. So you need to definitely look at the things a little bit more holistically here. And totally agreed. I would not feel comfortable printing the pellets and fuel rods and something like that. So definitely doesn't come to my mind. That's why iterating their design for additive manufacturing is I totally agree, definitely limited. And I would see it rather more holistically. What is the original intent which you want to meet? And you might be limited by the interfaces to the existing system if you want to replace a single component. So it might not be even worth to look into AM because the subtractive manufacturing might be the more suitable one. That's why, just to go to the next neighbor here, I want to see it together with reverse engineering, like 3D scanning and things. So if you want to go for spare parts, and then you have a decision if you want to subtractively or additively manufacture these parts. And you can explore the landscape in this kind of way and look then forward to see what is really suitable for that and what is not. And of course, we push that too, because you need to convince your management. And sometimes you just need to print something for the purpose of printing to show that it is a viable product, even if it doesn't make sense from a business case point of view. But in the holistic sense, I would say you need to definitely distinguish. And that's a big challenge for the whole industry, I would say. Like if you talk with contractors, they very often print parts where they say, actually, you don't need to print them, but because of lead times, availability of other contractors, especially post-corona, I shall say the world is still out of order here. Things might be a bit twisted so that you print more than what you actually need to print.
Correct. And then question number 11, I think that one is for you, Adam. What do you think of the use of AM to manufacture microreactor designs? Would you say such an application could foster the use of AM?
Yeah, certainly. I think I said towards the beginning of the talk, right? A lot of what we've done is adapting existing components to AM and saying, how can we improve existing designs? And that's there's inherent limitation in that, right? There's a box, a performance box, and a physical geometry box that we have to fit inside of. We can do some modification with AM, but with microreactors, specifically the Vinci microreactor at Westinghouse, right? That's much closer to a blank piece of paper where we can say what is the optimum geometry for this function, and what would that look like if we could print it. And so, yeah, I can't speak too specific, but there's certainly a number of applications we're looking at for AM to bring value to microreactors.
Yeah. And then I think number 12 is for Dr. Dehoff. Do you see a capability gap within Metal AM that you and your industry would like to see solved? Part size, resolution allows. Actually, all of you can answer it, but I would like to hear Ryan first.
Yeah, I think we've identified a gap where we think the qualification is probably the most important aspect, and having a method for qualification. And so we're focused very much on the digital side, to do that, combining in situ process data with modeling for predictive performance and trying to see how good are we actually at doing that today. And what do we need to, what other challenges need solved in order to fill that capability gap. When it comes to size and resolution, I think this is always a trade-off that the additive community has sort of had, right? We can make very, very high resolution components. The challenge is that they often take an extremely long time to make, and therefore your economics and your business case suffer. On the flip side, I can lay down a lot of material very, very fast, such as in DD processes, but the challenge there is that you don't necessarily have the resolution that you need over the entire component. And so I think to some degree, new systems coming out where you're integrating or getting the benefits or breaking that paradigm are beneficial, but I'm not sure that that's the limiting driver of what's holding the technology back.
Right.
And I could be wrong on that. I know I would probably say Adam and Benjamin have more experience in terms of implementation, and I'm more on the research focus. So I know those are the gaps that we're trying to solve, but I don't know from an implementation standpoint if they see that that's true.
That's why I think Benjamin maybe can add something. Yeah. Right, Benjamin, or not?
Yes, sure. But yeah, the first point, definitely I need to repeat what Ryan said. The qualification certification aspect is there. So if we do not have the code basis for that, but there's another huge gap for us as a utility. We need to have the ecosystem here around with us. So it doesn't help us looking only at the contractor who does the printing of a specific part which may be redevised. We need to look at the whole supply chain there, looking from the powder. How does the powder actually get quality assured, and how does this all tie in into the whole supply chain until we get the part, including post-processing? And there was a question also on hipping. I'm very split on this. There's some good cases, there's some really bad cases around that. So we need to not only look at ourselves as a utility, but we need to also look at our regulators. So in the nuclear sector, it's very, very important to pursue the balance of power. So you can have the best education and the best people on the side of the utility, but the regulator lacks the experience and the knowledge. So we're not going to go anywhere with approval. So you need to always look at it holistically. And there's so many gaps right now available here to be tackled heavily. So that I shall say, until we really adopt this in a convenient way where we just press a button and say, well, digital model XYZ goes to the contractor alpha beta, and we have the approval digitally by the regulator. That is still some very, very good work, but it shares resources with other digitalization projects. So a lot of gaps here, but a lot of gaps being shared with conventional challenges as well. So I think
Okay.
there's good work ahead, but we can do it.
Thanks, Benjamin. 7 minutes left to answer, the remaining questions. And question number 13 is from Ronnie. And I think, Benjamin, you're already out of out of the table for this one, since you're a very big fan of LPBF. So Adam and Ryan, are you already using RDD for big parts?
Yeah, as I touched on, that's something that's starting to happen more and more. We don't have a part in application right now using wire art, but certainly an interesting area, and I think there have been one or two applications that have come out at this point. So definitely see a lot more activity in that area in the near future.
Okay. What about you, Ryan?
Yeah, we're doing a lot of work on large scale additive manufacturing. It doesn't happen to be for the nuclear industry today, which is a little bit unfortunate, but we're trying to go that direction. We've been developing a lot of technologies. We actually worked with GKN, which is an aerospace supplier, to do some titanium deposition, and they're moving towards production in aerospace. We're also working on the development of a lot of DED technologies and trying to look at how do we help organizations like EPRI and ASME go through and certify and qualify those materials. We've made a lot of large scale parts like impellers and valves for a host of different organizations. I'm not sure we're doing that today in the nuclear industry holistically, but I've seen some good example cases across the industry where nuclear is going that direction, and I think that they believe that there's some really good applicability to the industry for that technology.
Okay, good. Question number 14. Are you using HIP as post-treatment? This is a very interesting question. Benjamin.
Yes, I touched briefly on that one before. So the hot isostatic pressing is by research a very, very good opportunity. Personally, I had some bad experiences with that. So it really depends on what you want to achieve. And many materials rather benefit from a conventional, or many parts, I shall say, not materials, but parts benefit from a conventional heat treatment, a properly done and properly designed one, more than they benefit from a hot isostatic pressing. So definitely not entitled to give a full disclosure here, but I would say it depends on the application case, and you need to look into the details, which material, what kind of design properties you're targeting, and what kind of wall thicknesses you're having. And you need to look into the process a bit deeper itself, making sure that it's only for your component filled in the autoclave and not obstructed and all these kind of things. So you need to make sure that you know what you're doing here.
And Adam, and then we'll jump to the conclusion.
Yeah, I agree with that. Yeah, 100%.
Okay, good.
See the opinion too often that, you know, if you're doing AM, you have to be hipping, and that I disagree with that strongly. Yeah, you've got to look at the material and the application, and does HIP actually provide a benefit there? Because there's a lot of circumstances where it's not necessary, and it's just becomes another cost inhibitor to doing AM. The other thing I'd add is also take a look and make sure that if you do HIP something, it stays hipped once it goes into operation, right? Especially if it's in a hot environment, make sure that it's not undoing the HIP essentially, which can also happen.
Okay. And then just to conclude, because we have 3 minutes left, I would like you to, have a short, word on standards before we close this session. So the standards that need to be revised, that need to be improved in order to foster the use of AM, and then we'll be good to go. I will start with Ryan for this one.
Yeah, I think the community holistically getting involved in standards is always a really good thing to do. I think we're starting to see more standards come out. I think using the information and the digital data that's coming out of additive will be a great way. I'm not sure that we know how to do that in a standard quite yet. But I think having the community come together and try to understand what's the best way to do that is something that could be really beneficial to the industry. And so, looking at how we do that, I think people are always hesitant to share data sometimes, but I think that's the direction that we need to go.
Yeah. Benjamin, and I think you can try to answer the question from Pranav, by concluding, because he was, he added a comment for you in the chat, in the Q&A chat.
Yes, so for our primary circuit, we heavily rely on the ASME boiler and pressure vessel code. So that is something which needs to be tackled head on, that you adopt these AM manufacturing methods in the code, that you can design according to the code rules for the utilities. The other side, of course, is we have the Swiss regulatory landscape here, as same as the NRC provides for the US. We have the ANSI providing for Switzerland. So that is all these standards which need to be adapted here too. And we have specifications for all the products which we have here conventionally manufactured. So these need to be all revised and encompassing in the way that you adopt the AM challenges. And just to touch on what has mentioned with the ISO standards. So there's a chain, there is a nuclear law, there is the guidelines enacted by the regulator, and then the quality assurance systems of ours, they adopt the different standards, which are from the higher levels and link them to the lower levels. So there's ISO standards, ASTM standards, the Euro norms, and so on and so forth, Swiss norms. But to make it holistically work, you don't need to revise all of them. So if we have ASME boiler and pressure vessel code adopting the additive manufacturing world, and the Swiss regulatory body enacting the guidelines which allow the adoptance of these AM methods, I think we have a good starting point here.
Thanks very much. Thank you very much, Benjamin. And last but not least, Adam.
Yeah, I don't see standards at present as a huge hindrance for the adoption of AM in general, right?
Okay.
No, I agree with everything that was said, right? I mean, ASME boiler and pressure vessel code kind of is like the last big piece, I think, that really opens up a whole new realm. But outside of that, in a general sense, right, the NRC and other regulatory bodies have been extremely collaborative and extremely nurturing in wanting to facilitate AM, right, rather than be a hindrance and come in and put all of these additional new, very specific requirements on top of it. So, like from the NRC's perspective, right, they issued what they call advanced manufacturing AMT guidelines, advanced manufacturing and technology guidelines, right? So instead of slapping down all these additional specifications and industry documents, it's more of a practical list of here's the important things that you need to demonstrate that your part's good, that it can safely operate. We're not going to specify how you have to do those things, but here's the types of things you need to demonstrate and prove to us. Go do that in the way that makes the most sense, and that's a big deal. That's really huge in terms of really safely enabling, practically enabling the proliferation of AM and nuclear.
Well, that's it. Benjamin, Adam, and Ryan, thank you very much for joining us during this episode of Additive Talks. Thank you for sharing your insights. I'm sure they were actually valuable for the audience. To the audience, thank you for listening to this episode of Additive Talk session. Please stay tuned for the next panel, for the next session that will be announced soon. And be assured that get sure and stay tuned on our social media. The recording of this Additive Talk session will be made available very soon. And yeah, that was it. I now wish you a very wonderful end of day. Stay tuned and stay safe wherever you are in the world. Thank you.